Hello everyone, in this video under process synchronization we will see semaphores. So semaphores is a synchronization tool which is used for which is used by synchronization. As semaphores, there is an integer value called s, and this s value can be accessed via two individual operations at a time. So if there are two processes which needs to execute critical section at once or critical section problem at once, then to give the access for critical section, the value of s is introduced. So we have two operations under semaphores. One is wait value. So wait value makes the s value, that semaphores, the wait function makes the semaphores value to decrease, or it will decrement the value, and signal operation will increment the value. So wait operation, under wait we have wait for s. While s is less than equal to 0, you should again decrement the value of s. In signal operation, increment the value of s. So continuing with semaphores, we have integer value that can range over unrestricted domain. So binary, we can take the s value which is of binary value, which is in between 0 1, or we can go for semaphores value of unrestricted values, like it can go from 0 to minus 100 or plus 100 or any unrestricted value. The semaphores which is having binary value, that is 0 or 1, these type of semaphores we call it as mutex lock. In mutex lock, the wait makes the semaphores value to 0 and signal makes the semaphores value to 1. So to solve various synchronization problem, we can make use of semaphores. Consider we have example like two process where it requires two semaphores value, that is s1 and happen before s1 requires to happen before s2. For creating semaphores, we need synchronization initialization to 0. So we have a process P1 which is waiting for a signal sync, and P2 waits P1 signals sync ch and P2 waits for sync ch, that is s2. So under the process, the value or the name of the semaphores is different, but signaling the values which is returned by the function are same, they will pass the parameter while calling the function. Can implement the counting semaphores as a binary semaphores. So we have implementation of semaphores here. So as I told, for the semaphores we have two functions, wait and signal. So under signal operation we are incrementing the value of s, under wait operation we are decrementing the value of s, because continuous wait will decrease continuously s value, and if I come for signal operation, then it will signal the process that the process which is under critical section has come out for reminder section. As implementation of critical section is allowed only for one process at a time. So the other process can be executing with reminder section. I can take P1 under P1 process under critical section and P2 process and reminder section. Once the P1 process enters into the critical section, then it will call the function wait. So once the wait function is called by process P1, the value of s will keep decreasing until the critical section is executed. If the critical section or the wait mutex is called loop wise, then the critical section or the wait value will be reduced based on number of loop the function is working. If it is only once, then the s value wait function called once and the s value is replaced to 0 or minus 1. Once the process P1 completes the critical section execution, it calls signal. Once the function signal is called by passing the s value which is altered by wait process, that will be incremented. So if the S value is incremented, then the process P2 can acquire the critical section problem. So based on the semaphores value which is passed as mutex, like here we are considering the value as 0 and 1. If we are having mutex, which is binary semaphores value, and this is how it is given for critical section problem, where synchronization is achieved based on wait and signal module. Next is semaphores implementation. As I told, must guarantee that no two processes can execute wait and signal on the same semaphores at a same time. So you can make use of multiple semaphores and multiple functions to execute wait and signal, but if I am using only S as a semaphores, then there should be only two processes which are using wait and signal process at a time. Thus it implementation becomes the critical section problem, where wait and signal code are placed in a critical section. Could now have busy waiting for a critical section implementation, but implementation code is short, like the semaphores value like signal and wait function are very small. It doesn't take much time. Little busy waiting critical section for rarely occupied category. If the process the P1 process is occupied critical section for longer time, then the waiting time of the process P1 becomes more, like whichever the process which is under the critical section should execute the code fast. To do that, the semaphores is implemented only for the shorter code of the shorter code category of executions. That applications may spend lot of time in critical section, then it is not a good solution. Semaphores is not a good solution where you have a critical section problem with a very big application. Then it is not a good solution for choosing semaphores. So if at all the busy waiting is, if there is no busy waiting for a critical section, we can go for semaphores. With each semaphore there is an associated waiting queue, which enters in the waiting queue has two data items. One is value, that is an integer, pointer where you have a next record of the list. So these two operations can be done based on block and wake up. So block means the operation will be like the block operation will be invoked by operating system for those processes which are under waiting. And once the process releases the critical section, for the next process to be executed, operating system calls wake up function so that it can acquire critical section problem. To do that, we have a typedef structure, int value, structure process, a list of all the operations, and then semaphores value. Based on the semaphores value, blocking the queue and wake up the queue is done. So implementation with no busy waiting, like here we have no busy waiting where we have block and wake up operations. This is the implementation for that. Wait for the semaphores S and signal for the semaphores S are the two functions like semaphores what we have. S value will be decremented in wait as we know, and S value will be incremented in signal as we saw before. But today for the queue of process to be acquiring the semaphores value, we have block function and wake up function. If S value is less than 0, then add this process to S list, means all the process in the S list will be blocked. If the S value is less than or equal to 0, then remove a value or remove a process from the list of process which were blocked, and that single process will be waked up. Instead of waking up all the process in the list, one process from the list which has to be executed next will be waked up. So next we have deadlocks and starvation. Since there are the process in the list because of process waiting for execution, like a long waiting queue. The process go under starvation. Deadlock is like two or more process waiting infinitely for an event that can be caused by one and waiting for that process, but that process never finishes the activity. So that condition is like deadlock. Take an example of process P1 and P2 which are waiting for the process P3, but P3 process never completes its execution. P1 and P2 process go for deadlock stage because it never gets the execution. Let's consider we have S and Q as a semaphores value. There is a condition for P0 which is always waiting and P1 which is always waiting, because P0 process is waiting for the semaphores S and P1 is waiting for the semaphores Q, where if you take in the other way, P0 is waiting for S and Q and P1 is waiting for Q and S. Without releasing the Q, without releasing S, P0 cannot execute. Without releasing Q, P1 cannot execute. They have under a situation where one is dependent on another and the another one is back dependent on one. This condition we call it as deadlock. Starvation is like infinite length of block. We have seen block and wake up function. What if the blocked list of process is not worked up for infinite time, like a minute, 2 minutes, 10 minutes and so on? If it is not invoked, then we call the condition as starvation. Priority inversion is the scheduling problem when a lower priority process holds the lock needed by a higher priority. It's like a emergency is there, but the execution is taken care by the normal process. It is also a process which is running under program, but there is an emergency process with a higher priority, but the normal process is acquired the lock and it is not releasing for higher priority process. That is priority inversion. So I hope you understood these topics. Thank you.